Thanks everybody for showing up and coming here. We've got a great talk for you. Our next speaker lives on a farm, but he's here to talk about functional and imperative programming. Please welcome Ben Hindman.
Awesome. Thanks so much. All right. I'm going to be talking today about a new programming framework, in particular the programming model that we built inside that framework. It's called Reboot. A fun play that I'm going to come back to throughout the talk is this idea that as part of the programming model, we're taking a lot of ideas from functional programming, but the code that developers end up writing feels very imperative in nature. So it's trying to meet developers where they are, let them write imperative-like code, but ultimately the applications that they end up building are very, very, very functional. This is my first time to LambdaConf, and I guess it'll be my last. So I thought I'd start a little introduction about myself. I'm Ben. In a past life, I was the creator of a piece of technology called Apache Mesos, which was one of the first container orchestrators that really helped ignite the container and microservices era. And ultimately, Mesos, I think its history is that it's really like the BSD of Kubernetes, where Kubernetes kind of became the Linux of container orchestration. But it saw massive adoption across big companies like Twitter, Uber, Netflix, Apple, PayPal, tons of companies. Still to this day, just like BSD, runs on millions of cores. I co-founded a company out of that called Mesosphere. We did lots of cool things in the container orchestration space. Probably my favorite thing that we did was we hosted IceCube at KubeCon. And that was really fun. If anybody happened to have been there, it was yeah, you were there. Awesome. It was a really fun time. Yeah, exactly. Ain't no party. Yes. I was one of the founding board members of the CNCF and served on the inaugural TOC. So got to spend a lot of time with a bunch of companies as they were adopting cloud native ideas and building cloud native apps. And based on all that experience, now I'm trying to rethink how we build applications for the cloud with reboot.dev. So cloud native state of the art. We saw this big giant evolution from monoliths to basically composing together microservices and lambdas. There's a word in there that I think is really important, which is composition, right? As functional programming people, composition is a good thing. And there is a lot to like about microservices. When I talk about microservices, if I use the word microservices, I'm pretty much referring to microservices or lambdas or any of the variants in there. I'll probably just say microservices, but you can assume I'm talking about all of them. So there's a lot to really like about them. The modularity of building microservice-based apps makes it easier to understand them, to modify them, to test them. It gives organizations engineering agility because teams can operate and deploy their software more independently and autonomously. It enables technology diversity if your company wants to support that behind well-encapsulated APIs. And ultimately, it's easier to scale. Makes it easier to scale the company and easier to scale the applications. There's a lot to really like. That all being said, in all the time that I spent with trying to help organizations adopt things like microservices, building full-stack apps using microservices is hard. And there's a lot of reasons for that, and it's one of the things that motivated trying to come up with a new programming model. But ultimately, it sort of created this stigma in the industry where microservices became the architecture that people were told not to start with. There's a famous quote from Martin Fowler who said, you shouldn't start a new project with microservices even if you're sure your application will be big enough to make it worthwhile. So the conventional wisdom became, instead, that you should only adopt microservices when you graduate off of monoliths. When your product and company are scaling like crazy, because that's the perfect time to rewrite everything. And that continued to be a trend of a bunch of companies that we ended up working with, which is really, really unfortunate. All right, so the setup for this talk is we're trying to help organizations that are building full-stack apps, okay? So full stack means something like an e-commerce site. Specifically for this talk, React-based front ends, you'll see why later. But people that are trying to build reactive, interactive, full stack applications with UIs. We want to not have to have some pivot point for organizations. We want the application to be scalable from day one. Even if 90% of the apps that get built out there don't need it, we don't want developers to have to rewrite their apps when they do. And really, we want to try to make sure that we don't conflate deployment boundaries with logical code boundaries. So it should be scalable, but hopefully you shouldn't feel it when you first start out. And then finally, safe. I mean, one of the reasons why microservices and Lambdas are so challenging is because of the fact that they're distributed. And I'm going to talk about some of those bugs. But ultimately, we want to try to solve some of those bugs up front as part of the programming model so people can write safer code right out of the gates. Okay? All right, so we built Reboot. It's an application framework with a novel cloud-native programming model. That's what I'm going to be talking about today. It's not a new programming language. We've specifically trying to target existing programming languages. So far, we built it for TypeScript and Python. So everything we're talking about today is real. You can go download it. You can play with it. We hope to expand to other languages in the future. All right, the good stuff, the programming model. So from 100,000 feet, Reboot is really three things. It's data, it's functions, and it's an execution and composition semantics, which hopefully for this audience should sound like a good place to start. So let's start with data. Reboot data is typed. So again, we're targeting cloud-native applications. So you describe your data in Reboot as a schema using an interface definition language. Okay, we started with protobuf, but we'll support OpenAPI or other interface definition languages in the future. Okay? Why do we do that? Because we want to support applications being built, again, going back to some of the values of microservices, out of many different programming languages in many different environments, browsers, as well as in servers, so forth and so on. So an example that I'm going to use throughout a lot of the talk is like a bank app. And so you could imagine that we have something like an account. An account has, the name, birthday, balance, all the other things you would imagine you'd have inside of a bank account. All right. Reboot data is durable. When you construct a new instance of one of these data types, it's persisted, and any state updates you make to it are also persisted. There was a great talk yesterday about orthogonal persistence, for those of you that went to that talk. This is an example of a system that gives you orthogonal persistence out of the box. You are not responsible for trying to persist the data. It's persisted for you, and you're going to see examples about that. Okay? All the code examples I'm going to give here are going to be TypeScript. And so this is actually effectively instantiating an account by calling one of its constructors open. I'm going to talk about functions in a little bit. All data is addressable. So when one of these instances actually gets constructed, it has an address. It has an ID. So every constructed instance has a unique ID, which you can use that ID to actually get a reference to it so that then you can call functions on it. All right, so here's actually looking up an account by passing in the account ID. All right, and Reboot data is partitioned. Okay, again, that kind of gets back to the setup. We want this to be a scalable system. So given all the constructed instances, they may live on different machines. So if I construct a bunch of accounts, they may live on a whole bunch of different machines. Okay? Really, this part is something you don't need to care about until you do. And there's lots of places that you may care about it, and there's things that we've built into Reboot to support that. But that's out of the scope for this talk. Okay? All right, so that's data. From 100,000 feet, moving down a little bit. Let's move over to functions. Reboot functions are typed. So just like data is described in the IDL, the functions are also described in the IDL. So for account, I have things like deposit, withdraw, balance, open, so forth and so on. They're also qualified. In particular, their execution and composition behavior is specified explicitly. They're qualified as either readers, writers, transactions, or workflows, and I'm going to talk throughout the rest of the talk about what that means. So I'm not going to go into it in too much detail right now, but they're captured in the IDL just via some annotation. You could imagine any IDL that supports annotations, it would be captured in that way. All right, so Reboot program model, data and functions. Now the good stuff, the execution and composition semantics. So I'm going to talk about the execution and composition semantics by really going through some of the things that really motivated how we thought about building Reboot from the start. And the first motivator I want to talk about is effects. So the problem which I'm sure is not lost on this audience at all, is effects and non-determinism makes code hard or harder to reason about, and thus harder to compose, which ultimately at the end of the day is what we were doing with these microservices. They're also inevitable. They have to occur. Good programmers, we tend to naturally isolate our effectful computations, or we use constructs from our programming languages to actually do that. In Reboot, there's a well-defined execution and composition semantics, so I'm going to talk about that now, based on the different kind of qualified functions you can have. So the first function that I mentioned earlier is a reader. So it's something like balance on a count. Again, this is going to be TypeScript examples. The way you actually implement the functions for one of these data types is as part of a class. So this is, we call them servicers. They're the code that's servicing any requests for particular account instances. And this is just an example of the balance function. So it's a reader. It was annotated as being a qualified reader in the IDL. So how do readers work? Readers take immutable snapshots of state. So they can't be updated. Because they're immutable, we can execute them concurrently. We can execute many readers at the same time. And readers can only make calls to other readers. Okay, we only want them to make calls to other readers because we're trying to constrain the effects that these functions might have. And then, of course, they return a response. Okay, so they get passed some state. That state represents the data type. So we looked at it before, state.name, state.address, state.balance, whatever the other fields are. In this case, we can read the fields out, but we can't actually make any updates. Okay? Reboot writers. Again, we annotate in the IDL that this function is a writer, and then we implement it. So deposit naturally is a writer. Like readers, writers take the current state, except writers are doing mutations. So they get executed one at a time. By one at a time, I mean there may be many different accounts that are all running at the same time, but per account, only one writer method is executed at a time, not one writer across all the accounts. And they update their state. So in a writer's case, if I'm doing a deposit, naturally I'm incrementing the balance. Like readers, writers can only call readers. Because if writers could call writers, then as we'll see in a little bit, we get the possibility of having partial state updates across different accounts, which we don't want, right? We're trying to constrain the bugs that we get from distributed systems. We'll talk about how to solve that in a little bit. Of course, since writers can only call readers and readers can only call readers, then inductively we know that we're in a good place, and the only state updates that can occur are the state updates that are specific to the writer. So when does that state update occur? The state is automatically persisted if and only if the function returns a response. So this is the orthogonal persistence part. You update the state, you return a response. If you don't raise an exception or throw an error, whatever it is, then that state will be persisted, and those effects will take place, and we'll return a response. Okay? All right, so how do we enforce the semantics? The first semantic we want to enforce is that we can only call loud functions. So I said readers can only call readers, writers can only call readers. How do we enforce that? We do that by requiring that all function calls that are made require passing the provided context. So in addition to the state that gets passed to every one of these functions, a context is also passed. And you might have seen it before, but in balance, a reader context gets passed. And in deposit, a writer context gets passed. So with that writer context, whenever I want to call a function of one of the other data types, I must use the context. I must always pass it. So if I were, for example, to get a reference to some other account and then try to call a function on that account, I would get a type error. If in TypeScript I'm using something like TSC, or if in Python I'm using something like MyPy. Why? Because I can't call a writer method, which is what deposit is, with a writer context. I'm constrained. Okay? If you choose not to use a type system, then we'll raise a runtime exception. But at compile time, you can make sure that you are following the semantics of what you can safely call. Okay? What's the next semantic we want to make sure we have? Well, that there's no other side effects. Right? What if I'm calling out to external services or I'm doing all sorts of other things? Right? The only effects that I want to have happen in the method is, in the writer's case, just updating the state, or in the reader's case, no effects. So how do we make sure there's no side effects? During development mode, which is a version of when you're running your reboot application, say on your laptop or in some cloud machine, we execute every function twice. So for those of you that are familiar with React, this is inspired by strict mode in React, which is a mechanism that helps people find when they are making effects that they don't intend to have. And it's just one of those things that just works. This is an interesting philosophical debate that I'd love to have with people over beers later in the day. But again, our target is really existing cloud-native developers where they're at, building Python and JavaScript. We're not inventing a new programming language here. We're trying to introduce a new programming model. And this idea of strict mode has been wildly successful for a lot of developers, so we employed it here as well. Okay, so how do we make sure no other side effects? We execute the function twice. People find out really, really quickly if they're calling into external things, real quick. Okay? Anyway, fun philosophical debate. Love to chat with people about it over drinks. It's something that my very rigorous graduate school static type mindset took a long time for me to be like, wow, actually, this is a good solution. Okay. So title of the talk was imperative locally, functional globally. And I want to get back to, again, this writer function where the code that you're writing feels very imperative. I'm literally updating the state. I'm mutating the state directly. But as I start to compose a bunch of these pieces, I'm getting a very functional experience. Okay, and we'll see that again. All right, moving on to motivator number 2, real time. Okay, so getting data, getting real-time updates out of state that's spread across tons of different microservices and lambdas is so challenging in a lot of these environments that it's prohibitive. Because it's not just about calling one microservice, it's about that microservice actually getting data from another microservice, so forth and so on. It tends to be so challenging that most organizations just don't do it. React was a huge inspiration again for us. React solved this for the front end by being able to isolate effects, which, as we just talked about, we do with Reboot as well. So Reboot actually provides first-class reactivity for readers and later workflows I'll talk about directly as a primitive. So what does that look like? So I'm going to switch gears a little bit from the account type to a bank type. And you can imagine that there's a function on bank type called account balances, which gets all the balances across all the accounts. Okay? So what does it do? Well, first it looks up another type, which is a list of all of its accounts. It gets the last page, because you can imagine we're trying to just show this on a website. We only want to show the last page. It gets the last page of accounts that have actually signed up. And then it loops through all those accounts and calls out and gets the balance of each account. Okay, it's a toy example, but it's meant to demonstrate the functionality. So as this function executes, we can determine the DAG that represents all the possible state that may be updated that would cause us to want to re-execute this function if the state ever changed. In particular, as we loop through all these accounts, we're effectively saying, oh, okay, yeah, well, here's an account where state might change. Oh, here's another account whose state might change, so forth and so on. In fact, it's not just the accounts. That list type, which is effectively just a type in Reboot that represents a distributed list. It's implemented however you would imagine implementing a distributed list. Also has state that might change, that if it changed, for example, a new account got added, you would want this function to get re-executed because you have a new account that you need to display to your UI. Okay? This is LambdaConf, so naturally I had to not use a for loop and show you the example using map and reduce and running it in parallel. There's the example. A little bit easier to read for a lot of people. Maybe it's easier to read for y'all. There it is. Okay, so how to actually call the function reactively. Thanks to the IDL, we can actually generate React hooks directly. So that IDL tells us all the information that we need to know, hey, these are the readers that you can actually call reactively. So we have something that gets generated called useBank. And on a bank type, we have something called generated that gets useAccountBalance. The use in the front there, for those of you that are not familiar with React, is the convention for saying that this is a reactive call. Okay? So just like any of the other pieces that are reactive in a React UI, useAccountBalances is now reactive. So with one line of code, if the state ever changes in the bank, or in the list that it's talking to, or in any of the accounts, we'll re-execute all those pieces, propagate that information all the way back up to the front end, and the front end will re-render. So all the machinery of WebSockets, retries, connection management, exit is all handled in this one line of code of just useAccountBalances. Okay? So again, I want to keep coming back to this, imperative locally, functional globally. We haven't had to set up streams. We haven't had to set up any of these other constructs. We've written extremely imperative-looking code, but ultimately we get a safe, reactive experience. Okay, all right. So reactivity, first-class concept. All right, moving on to motivator number 3. The network's unreliable. And the apps that people are building are distributed. There's a great article from, I think, 2011, which is an ACM that was, whether you like it or not, you're building a distributed system. It might have even been from 2009. For those of you that haven't read it, it's a great article. And they were talking about a world with monoliths. The distributed system they were talking about was just the front end and the back end. And we just made it way more complicated when we added microservices and lambdas. So we've had all the problems of building a distributed system between the front end and the back end, and we just made it even more complicated. And these are real bugs. I take screenshots of these bugs all the time because I find them fascinating, but they're real bugs. This is me trying to deposit a check on my phone. I got a failed to deposit check with a little dialogue, okay, or would you like to try again? I was trying to deposit my check, so naturally I clicked try again. It worked. 24 hours later, I got this nice email. We were unable to process your mobile check deposit. Okay, gave him a call, followed the instructions. Nice lady at the phone politely accused me of bank fraud, which is a felony in certain states, for my $219 check. I remembered the experience and just kind of chuckled and said something, exactly once Semantics, and said I was definitely not trying to defraud the bank. They fixed it. We have this retry paradox in distributed systems, which is that we want to retry calls in the event of a retriable error. Because it's retriable, like the network, like we don't know what happened, right? But we can't retry if the call has effects because we want to make sure that that effect is only performed once. Right? This is what leads to all of these websites out there telling you things like, please don't close this window, or use the back button, or yada, yada, yada. Because they can't handle the fact that if something bad happens, they can't retry. It's not safe. This is the state of the art. Okay? So the observation insight is you want to retry, you just need to know whether or not you've performed the effects or not. Like a lot of the things in Reboot, there are ways in which we've solved this in the industry, and we've tried to take those things and codify them and put them into the system. And the way that we did that in Reboot is we made item potency a first-class primitive. So item potency is built into the programming model, and I'll explain what I mean by that now. So again, getting back to some calls being made from the front end in something like React, I can use account, and then I can do something like account.deposit. When account.deposit is called, it is always called idempotently. The user doesn't know about that. They can, of course, adjust the idempotency contents if they want, but by default, all calls are made idempotently. What the system does under the covers is when it receives a call that's been made idempotently, it stores the idempotency information alongside the effects. Okay? The developer doesn't have to do anything. They don't have to the function looks exactly the same. You don't have to do anything else. It's still just, the deposit function that you saw looks exactly the same. As I said, the code-generated React bindings call all functions by default idempotently. And this lets the clients retry forever. Because now what the system does is before we hand off a call to the user's code to actually execute, say, something like deposit, we first check to say, hey, have we already performed the effects from this call? Now, again, we're going to rely inductively on the other properties. So we know that the effects are complete from the perspective that if it's a writer, it only has its effects, its updates that are happening. There's no partial updates that potentially could have occurred. So when I persist the state update for the writer, I can also simultaneously persist the idempotent information atomically and make sure that when I check whether or not this mutation has occurred, it's occurred or not. OK? All right, idempotency. All right, moving on to motivator number 4. Data invariant inconsistencies. What's the problem? Machines fail. This was probably the thing that motivated me the most to think about trying to come up with a new cloud-native programming model. And so I'm going to spend a little bit of time motivated for you all as well. All right, so we talked about e-commerce checkout as being a great example. This is what you'd imagine a checkout function might look like. I have a cart. I try to get the items. Once I get the items, I try to figure out the cost of shipping and make sure I can ship the order. Then I authorize the charge. Then I actually ship the order. Then I clear the cart. Then finally, I send an email to say, hey, we're all good. We sent it. When you first look at this code, again, it has a lot to like. Independent teams can own different services: cart, shipping, payment, emailer. I'm just composing all these function calls together. That's allowing me to do more by taking all these different services that exist and do what I want to do. But there's a massive problem with writing code like this in the cloud-native microservices or Lambda-based architecture. Which, of course, the problem is, what happens if the machine fails after we call payment.authorizeCharge? So anybody that has run microservices in anger would not do this anymore. And there's really kind of two camps of people when I give this example. There's the first camp of people that are sort of like, yeah, Ben, move on. Like, nobody would build microservices this way. We know this. Like, I don't know why you're telling me. And then there's the second group of people that are like, oh my God, I wonder if my software that I'm running right now in production has these bugs. It's totally understandable that a lot of people fall into that second category, because this example that I showed you, developer's intent here is that, of course, this gets executed atomically. That's what we're used to when we compose things. And of course, idempotently on retry, which is the example we already talked about. But again, it's not wrong that people would fall into that category of, oh, I might have this bug, because this example comes straight from Google's microservices demo. Everybody that starts building microservices from Google's microservices demo, which is most people, are bound to write code that is going to have data or invariant inconsistencies due to failures at a bad time in their methods. Not a great place. And these are real bugs. Again, I like to take screenshots. This was me trying to book a flight. I got an unable to complete transaction. Naturally, I clicked OK. I tried again. I got it again. I changed my credit card. I tried it again. I got a failure again. I changed my credit card. I tried it again. I tried it 4 times. I was like, wow, I think something's just wrong with United, so I'll just move on. A little bit later, I checked my email. I had 4 emails from United. I was like, oh, that's an important message regarding your reservation. I didn't have any reservations. But we all know what happened, right? The code executed. It got through to a point where it was sending out emails, checking things about. It had gotten past the place of creating reservation numbers. I had 4 different reservation numbers. It had probably hit some service that was like, create a new reservation number for me. Then it was hitting another service that was like, check to make sure reservations don't overlap. That's what this email's about. So I got 4 emails telling me that the reservation has a problem, but I never ever got a reservation. These are real bugs, okay? So again, we've tried to solve these problems. We've tried to move from an inconsistent world, where you have partial state updates, inconsistent, to an eventually consistent world. That's the state of the art, really. We've done that via what we like to call the rise in ubiquity of queue-glued software. So we've realized that we can't just call between all these different services safely. So instead, what we'll do is we will communicate between each services by writing to a queue. So we'll safely write to a queue, hey, I've done this thing, you need to do the next thing, and then the next thing we'll try to read from the queue and go from there, and then that thing will read it, and it'll be great, and write to a queue, and then so forth and so on. And we're basically reinventing in the cloud this inversion of control that we're all familiar with from all the callback-based languages. Callback hell, effectively, is how most of these systems are ultimately built. Business processes scattered throughout the code base, hard to reason about things, hard to refactor, so forth and so on. At least, though, we get eventual consistency instead of just inconsistencies. It's funny that we have eventual consistency in such a strongly consistent world. We have these eventually consistent applications due to these queues, event sourcing, many durable execution-like systems. But the databases that are underneath them are highly scalable, highly distributed, and strongly consistent. So it's ironic that as we moved into this world where we've had so much research that's been done, so much good work that's been done on these highly scalable, strongly consistent databases, and yet all our apps are still eventually consistent. All right? OK, so motivator number 4, data invariant inconsistencies, machines fail. Effectively, what we're doing in Reboot is we're assimilating the database into the application. And if you went to the orthogonal persistence talk yesterday, you sort of heard that it was like, throw away the database, right? But if we do that, if we simulate the database in, we need to give developers a primitive for atomicity. And this is, by the way, where I diverged from the orthogonal persistence talk yesterday. But divergence is good. So how do we do that in Reboot? We provide first-class transactions. OK? All right, so let me now talk about what it looks like. So we've seen readers, we've seen writers, now we're going to talk about transactions. So I'm going to go back to the bank. We can imagine there's a method on bank called transfer, and this is what it would look like. What is transfer doing? It's doing what you'd expect it to do. It's transferring from one account to another account. So as I talked about before, writers can only update their own states. So now we're solving the problems of being able to update multiple states simultaneously that, again, may be distributed throughout the cluster. Okay, how do we do that safely? By qualifying your function as a transaction. Now I can go ahead and I can call withdraw and I can call deposit safely and make sure that either both withdraw and deposit have occurred or none of the effects have occurred. OK? Of course, I probably wouldn't write it this way. This is the way I'd write it if I was doing, say, an eventually consistent queue-based approach, do one thing and then the next thing, do withdraw and then deposit. But I've got this huge hammer now called transactions. So I'm going to do them at the same time. Because I can. Because I can make sure that they're either all going to happen or they're not going to happen. This is actually a really fascinating thing that from a lot of the apps that we've taken that we've ported over to build and Reboot, transactions as a mechanism actually allows you to write far more efficient implementations. So under the covers, of course, to implement transactions, we have to pay to do that, right? It's not a free abstraction. We have to pay to actually make sure all the different states that we're updating are only committed in a transactional way. But with that power, we can actually write our code differently. So that checkout function that was really getting the items from the cart, then preparing the ship order, and then all the other steps, can now do 4 of those steps completely in parallel because there's no data dependencies or any other kind of dependencies between those steps. So I've just turned a function that was originally 1, 2, 3, 4, 5, 6 round trips in the data center to 3 round trips in the data center, plus 1, which is the work that I actually need to do to pay for the two-phase commit.
Where's the transaction here? I don't see transactions here.
You're right. I did not forgot to make the context be a transaction context and put the state in. Thank you for finding a bug in my slides. I just took the code from the left and put it on the right. But in Reboot, exactly, you would have, the context would be a transaction context, and you'd have the state. Okay? Everything else stands. All right. Again, kind of coming back to this model, imperative locally, functional globally, this code for transfer looks basically identical to the code that you would write in your CS 101 class when you're first learning programming. And that's the goal, again, what we're trying to accomplish. But when you compose all these pieces together, you get a very functional experience. All right. So some of you might be asking, hold on a second. That whole thing you were doing at the bottom, and there's going to be more bugs in this code because I clearly just copied this and it's missing transaction context. So just assume that it says transaction context in those spots. Okay. That emailer.send order confirmation, how do you do that? Isn't that an external effect? How can you send an email and if the transaction fails and you don't commit, how do I roll that back? Right? Great question. So the problem is almost all third-party APIs that we call out to actually have no support for any kind of rollback. And only some of them are compensatable. Some of them are, you can't roll them back, but you can call and say undo them in some style or in some way. And we need to solve this problem. To make Reboot realistic for the rest of the world, we need to be able to call into to external things. So for the observation or insight that we have in this model is that while most of those third-party APIs do not have any kind of rollback, some of them have a compensate-like mechanism, many of them have a dry run-like mechanism where you can check to see whether or not the operation that you were going to perform would have worked. And that has no side effects. So in Reboot, when you're trying to call out to external things, that's what you do. You dry run during the transaction, which doesn't have any side effects. But then you actually perform the external effects after the transaction is committed, making the external effects eventually consistent. So the effects within your Reboot application are strongly consistent. The external effects that you then perform later are eventually consistent. And I want to talk a bit about how this works because it rounds out the programming model. Okay? That's external effects today. In a perfect world, it would be very cool if in the future, companies could adopt and implement APIs using Reboot or a Reboot protocol. Because then my application could just call into Stripe as part of my transaction, and I wouldn't have to play this dance. We would have distributed transactions across the web. It's a big vision, but I think it's very possible. Okay, so the way that we actually perform external effects is using the last kind of function. So we got readers, writers, transactions, and now workflows. Workflows are the least constrained, the least safe, so in some ways have the most power, but also require the most responsibility. Workflows are like the code that we write today. By default, the semantics, which are a scary semantics, hopefully, as you're thinking more about them. It's the default model we have today. It's not atomic. It's eventually consistent. And what we do with workflows, though, to try to help developers get it right, is we retry all workflow calls upon failure. And we do this to try to help developers do what we call idempotent convergence, which is when you start to execute the workflow, even though it's not atomic, we want you to try to be able to converge idempotently on some ending state. Okay? It's the safe place to do external effects. And I put safe in quotes here because it's still up to the developer. They're still responsible for trying to idempotently do those effects in the face of retries, but we try to help with that. So I'm going to talk about how we try to help with that. So workflows, for those of you that have been watching this talk that are familiar with durable execution, workflows is kind of the closest thing that we have to the durable execution model that some other frameworks have introduced, i.e. not atomic, eventually consistent, retry and failure. But in all of Reboot, and also with the workflow methods, there is no replay log. And you'll see why actually not having a replay log simplifies some of the code evolution that you might want to do. All right, so here is an example of that wire transfer workflow. And so I'm going to walk through it. Okay, so first, workflows don't get state because they're not atomic. So you can't make any updates to state. When would we commit those effects? When would you see those effects? So if you want to actually work with state, you're effectively calling all the other methods that are transactions or writers. If you want to read state, you're calling readers. We've got some mechanisms to directly read and write state as well, but I'm not going to talk about it here. The most important point being that state's not passed in. All right. As I said, we tried to make some things easier in workflows. So we've got an until mechanism. Until is a helper for waiting for a condition. So you can imagine in a wire transfer, maybe one of the first things we want to do is wait for human sign-off. Right? We can do that via until, where until might call out to some different types to check the status of whether or not a human has signed off on it. The way until works is until will reactively, it leverages the reactivity mechanism in the rest of the system. It will reactively re-execute as long as a falsy value is returned. So if you return true or you return some actual value, which is not falsy, then until will fall out. Otherwise, it will reactively re-execute this only when the state that is part of the DAG that it's calling has changed. So just like the front end is only going to, pieces are only going to get executed reactively when any of the state changes, the until block is only going to get executed reactively when any of the state changes. Okay, so we're leveraging reactivity to perform this. So no replay log there. All right, under the covers, it also uses a memoize state type. This is just a state type that stores whether or not something has occurred. Anyone could do it. So most of this is actually not primitives in the system. It's leveraging other pieces of the system. Okay. The second piece is, you can imagine that you get the sign-off from the human, and then you want to actually withdraw the money from the user's account. Okay? So in a workflow, you have to be explicit about doing this idempotently. And the reason for this is because we need to retry. Okay? Because it's not atomic, and we have to retry. So it's very explicit in a workflow. Because if there's a failure after this point in time, as I said, workflows will be retried from the top. So what happens? We go to the top. We hit the until. Until has already been memoized. We've already successfully done the until, so we fall through. But we execute it. It's just a function that we call until says, oh, yeah, you already waited until this state, so you fall through. Then we hit the fromAccount.idempotently.withdraw. Just like when we retry from the front end idempotently, this is basically just retrying an idempotent call. It hits the backend. This is part of a backend, but it's in another backend. Withdraw says, oh, no, I've already done that. And so it just returns and says, yeah, great, I've already done that. Sure, here's the response from actually doing that withdraw. Okay? So again, this is eventually consistent. After I return from withdraw, the withdraw has occurred. The world can see it. It's not atomic across all these pieces. But it's safe in the presence of retries by just leveraging the idempotency primitive. So we leveraged the reactivity primitive for waiting for conditions in state. Now we're leveraging the idempotency primitive. Yeah?
Does your workflow survive, or does your workflow, if it gets interrupted, die, and then the middle of the workflow?
If it dies here at the X,
Yes.
we will restart it from the beginning. So everything is executed from the beginning. Okay? All right. Upon retry, again, we don't replay from the log. We just go through the steps that I talked about. And then we've got other helpers as well. We've got an at most once helper for calling to external services that actually are not rollbackable or compensatable. You'd actually have to write more code here where you deal with the failure if at most once actually failed. Let's hope that the third-party API you're using is not an at most once, because at the end of the day, you're in a tough spot if you have at most once. There's not much you can do. So we've also got an at least once helper if at least you have a mechanism where you can retry things idempotently. Say if you're calling out to Stripe, you could do that in an at least once where you use an explicit idempotency key to call out to Stripe safely and so on. So again, if there's failures, we restart everything from the very beginning. There's no replay log. We restart everything from the very beginning. But the big power about restarting everything from the very beginning and following these this idea of using idempotency information for what gets rerun and doesn't get rerun is it makes code evolution far easier. Because I don't care about doing effects in particular order. I actually care about whether or not I'm just doing these particular things. So I don't have an example here, but when you call idempotently, you can be more explicit about specifically what this idempotently call is for. So just like until has human sign-off, in idempotently you can say withdraw from account whatever it is. And you can move code around, you can do whatever you want, but that string is what guarantees that for this workflow, every single time I call idempotently.withdraw with that string, it will always be just that call to withdraw, not some other one. OK, same thing for mailgun message idempotently at the bottom. OK, all right, let me wrap up. So from high level, reboot programming model, it's really just data and functions and a well-defined semantics for how those functions are executed and composed together safely. Readers, writers, transactions, and workflows. We call the encapsulation of the data and functions in Reboot a durable data structure. And you saw examples of other durable data structures that we've used throughout the system. There's a memwise one, there's a list one. You can imagine you can build up these durable data structures that you can then share with other people and say, hey, it's just some library code that runs on Reboot. I can pull it in. I can run on my Reboot application. The program model becomes, instead of thinking in tables and rows in a database, you think in terms of these durable data structures that are distributed, that get partitioned across all the resources you have in your system. It provides first-class reactivity that can be used for reader functions and untils and workflows. First-class idempotency that eliminates the retry paradox and makes retrying methods the default and safe strategy, which again is amazing. Retries let you push the back pressure out to the clients. The more you can push out to the clients, the better. And then finally, it provides first-class transactions that enable composing effectful functions in a strongly consistent way. So I hope you found this interesting. Some ideas from functional programming that we're trying to incorporate in this cloud-native programming model. Like I said earlier, it's real. You can go check it out and play with it today. Check out our docs, join our Discord, ask questions, and we'd love to hear more about what you think about it. Thanks so much.
Fantastic. Any questions?
I'm kind of curious. So looking into local first software, where you don't know on the client side, like how long until your next internet connection will be valid for. Like it could be a couple hours until you can connect again. Have you looked into that at all? Like how does that play with that?
Yeah, it's a great question. One of the other movements that I think continues to gain steam. I mean, it's not like necessarily a new one, but it continues to gain steam is local first. And so there's a lot of different distributed models that people are trying to employ there. Probably the most well-known is CRDTs, right? CRDTs, conflict-free replicated data types. From our perspective, without going into a whole talk about the merits of CRDTs and the pitfalls and all those pieces, I think the real core of what Local First is trying to get after is the ability to give people a great experience when you're disconnected. That's something that the code that we generate for the front end can already do. So let me talk about what that looks like. Because we have idempotency, we can retry mutations forever. In fact, we can store those mutations in local storage, which for those who don't know what that is, that's a browser-specific thing. So you can close the browser, you can reopen the browser, you can go to that website, and that mutation that you had fired will still be there, and we can still continue to retry it. So it's a way of giving you experience of like, if you're using an app that has an offline mode, you get offline, you fire the mutation, we will continue to retry it even if you're offline until we can actually do it, okay? On the read side, it's very similar. The data that we've read via, say, something like use account balances, we can store and we can cache and we can show you, even if you've gotten disconnected, we can continue to show it to you. We have a local, we don't call it local first because we think some people are actually going down a very particular strategy for that. We call it disconnected mode. We have a disconnected mode that we believe for most of the apps you're building is completely sufficient. You know, you'd have to be disconnected for a very, very long time for all of your state updates to somehow run out of space to be stored locally that we can't send later. The real crux, and I won't waste any more time on it now, but the real crux is how you deal with conflicts. That's the real crux. And this is where I think, you know, there's a lot of, it would be nice if CRDTs just say did that well for you, but the reality is they don't. The reality is you have a lot of updates that are not associative and commutative. And if you have updates that are not associative and commutative, you need a centralized store to try to do those things. And we, in our experience, there's a lot more updates that are not associative and commutative, which means you need to try to fire those mutations once you reconnect. And some of those mutations need to tell you, hey, no, I wasn't able to do that thing because somebody else did it first. And so it all falls out in the way that you use the generated React code. Yeah.
Fantastic. We are out of time for questions. If you do have more, I'm sure Ben will be around in the hallways and such.
Totally.
But yeah, everybody, big hand for Ben. Thank you.